and he will discuss
hang on.
scattering amplitudes and gravity. Okay, please,
Sort of.
go ahead.
Right. So thank you very much for the invitation. It's a pleasure to be in Dublin, if only virtually for the time being. I will tell you about an interesting new approach to studying the gravitational two-body problem, which has been emerging for the last few years. So Einstein gave us a description of a gravitational interaction more than 100 years ago. And despite all the long time, we are still constructing a coherent picture of their classical and quantum pictures. There have been along the way many different approaches to both the classical and quantum theory. For example, people have been trying to use regular field theory, string theory, various world line approaches, twistors, numerical approaches, smart Ansätze. And it's fair to say that every single one of these approaches has brought something new to the table. It brought a different perspective and it emphasized different aspects of gravitational interactions. And each of them produced new results, but apart from direct applications of these new results, the explicit calculations that have been carried out expose structures and patterns, which in turn led to new calculational tools, which in turn leads to new calculational tools and new questions, which in turn made more explicit calculations possible. And this cycle has repeated a number of times, both in gravity, as far as gravity is concerned, but also as far as other aspects of physics are concerned. Now, and it's likely to repeat again in for the foreseeable future. Now, among the early predictions of GR are gravitational waves, which they are supposed to be ripples in space, or rather in space-time. And as they were originally constructed, they are in flat space-time. Now, they turned out to be very hard to detect, even though, of course, we've been having for quite a long time indirect evidence that they exist from the Halls and Taylor pulsar, for example. Now, the reason they are hard to detect is that the emitted power in gravitational waves is extremely tiny, and these things don't happen very close by. So if you were to construct an oscillator and put it on the table and let it oscillate, with that oscillator has mass m and then radius r and then frequency omega. If you plug in here numbers which are something that the table would hold, like a kilogram mass, a meter radius, and 1 kilohertz frequency, give or take, then you get that the power emitted is about 10 to the minus 30 watts, which is a little bit small. So luckily there are bigger oscillators in the universe. However, the power emitting gravitational waves is still tiny. So for the Earth sun system, we have barely enough to power 2 light bulbs, give or take. It depends on your preference of light bulb. But and the closest stellar binary would emit about 7 megawatts in gravitational waves. However, the detection is not exactly a detection of power, but a detection of a change in some kind of length. And that translates still into very tiny displacement. So if you have a rod of length d, then the dimensionless strain, which is the change in d divided by d, is more or less of this size has more or less this expression, and it turns out to be about 10 to the minus 23. So that's really tiny. If you take the Milky Way, this would be about an inch. So one would need to measure the Milky Way, the size of the Milky Way, to precision of about an inch to be able to determine gravitational waves produced by the closest stellar binary. However, not all people give hope that this is possible. And indeed, to great effect, recently we know that gravitational waves are real. And they have been detected by the LIGO and Virgo collaboration. And here are the signals that they've published. Now, on a more theoretical side, because gravitational waves are real, one might also expect that the quanta of the gravitational field are real. So one can, with a straight face, talk about perturbative quantum gravity, for example. Now, because of all these experimental developments, it's high time to revisit from a theoretical perspective gravitational waves and see what new we can bring to the table given the various advances in various fields of physics. So new theoretical input for observations is of course crucial, because the better we can model a signal, the more information we can extract from observations. The signal here, even though it's perhaps, well, it's intuitively clear that it has to depend on the details of the binary. So the better we can detect it, the more information we can extract about the details of the binary. Here, there are meant to be two black holes. There isn't much structure in a black hole, but if there were if there were neutron stars, for example, one could imagine extracting information about the structure of neutron stars from this signal. On a more theoretical side, theoretical input could also lead to theoretical progress. For example, as we are going to see later on, we're going to learn something about the structure of higher orders in perturbation theory. We're going to learn about some unexpected relations and generating functions of various observables in classical gravitational observables. And we might also learn about symmetries, which might not be visible from a Lagrangian point of view, for example. So this said, the method of choice will involve gravitational amplitudes, and many of the recent advances that happened in fields related to scattering amplitudes in the last, I don't know, 10 or so years. So the plan is to first talk a little bit about the anatomy of a two-body system, then talk a little bit about the relation between the scattering problem and the bound state problem, then talk a little about gravitational scattering amplitudes and how to compute them efficiently in the classical limit, by which I mean that we should compute just the classical part if possible, rather than compute a full amplitude and then toss away 99% of it and get the classical part out. And after all this will be said and done, we'll be putting everything together and we'll see some nice, well, it depends on your taste, but I would say nice expressions about two-body Hamiltonians, and we'll see what they tell us about LIGO. And we'll close with some hopefully wise words, which don't really belong to me, but hopefully they're wise. Right, so the anatomy of a two-body system and its time evolution. It's, well, so the spherical cow approximation is shown here. It's a really neat and clean signal, which is a little bit different from the one that's, from the experimental one, but no matter, if you squint hard enough, you can sort of see the features of the spherical cow in the signal. So it comes in three pieces. The in-spiral part, in which the two bodies are kind of separated from each other. They don't move terribly fast. Then, and because of this, one can imagine some sort of perturbation theory which is applicable. And this will be our playground for today. Then there is the merger part, in which perturbation theory no longer applies. One should deal with full-blown general relativity, all orders in Newton's constant, and so on, which for the time being is the realm of numerical GR. And then the end of the merger is the so-called ring down, which is again amenable to some kind of perturbation theory, except that unlike the first part, it's a different ground state. Here in the first part is Minkowski space. In the latter part is essentially Schwarzschild black hole. Now, if you look at the spherical cow and also at the signal, you will notice that there's a change in frequency of the signal, but that change is quite slow compared with the actual signal itself. So that suggests a separation of scale in which the conservative dynamics, which governs most of this oscillations, and the emission of radiation, which governs the change in the frequency of the conservative motion, are separated, so we can focus on one, namely the conservative part, which clearly dominates, at least for a while, and then tack on the radiation later on. Now, this will, of course, break down at some point, and we may be actually relatively close to the point where it does break down, but we will see exactly how this happens in a little bit. So let's talk a little bit about the part that will be our playground. That is the first perturbation theory. By the way, I should have mentioned, please interrupt me with questions whenever you have them. So there are two kinds of, or maybe three kinds of perturbative approaches to the in-spiral problem. The most extensively used, which is part of the LIGO pipeline, is the so-called post-Newtonian expansion, or the weak field non-relativistic expansion. It applies great for closed orbits for which there is a virial theorem, which says that gm over r is of the same order as the velocity of the bodies. So an expansion in Newton's constant will necessarily trigger an expansion in V because they're of the same order. So again, this is the post-Newtonian expansion. The post-Minkowskian expansion, or the weak field relativistic expansion, is what we might call in a normal field theory approach perturbation theory, right? It's an expansion in Newton's constant, but all the velocity dependence is kept exact. For closed orbits, one might debate which one is better. However, if one cares about open orbits, clearly the second one is the more suitable one, because there is no virial theorem. So one can have large velocities, but gm over r is still small. And this will be our main focus. So of course, post-Newtonian can be obtained by expanding in V later on. And then the last kind of perturbation theory goes by the name of self-force, in which both gm over r and v square are of order 1. The expansion parameter this time is actually the ratio of the two masses. So if you wish, it's an expansion around the probe approximation. I will have next to nothing to say about this, but it's a very interesting perturbation theory that's worth looking into. So post-Newtonian expansion has been used for a very long time, basically since a few days after Newton wrote down his potential, because anyway. Here is what's known. So the 0 or the Newton's potential sits here and has been known for a few hundred years. Then the first post-Newtonian correction was computed by Infeld and Einstein. And then the second, third, and fourth have been computed at various time intervals. The fifth order is still in the works, is almost ready as far as I'm aware of. There are a couple of terms that are still missing. But this is all that's known, and this is part of LIGO, at least up to here, it's part of the LIGO pipeline. By contrast, the post-Minkowskian approximation has a somewhat shorter history. The first order was completed at some point in early 80s, and it basically looks like Newton's potential times complete function of velocity. And then the second post-Minkowskian approximation was a few years later, and then the last two highlighted in red will be the subject of our story today. So again, this is mostly about closed orbits. So how does scattering fit into all of this? Well, the story is relatively straightforward. The idea is that the scattering and the bound state dynamics are ultimately governed by the same Hamiltonian. So if it's possible to construct that effective Hamiltonian from scattering and use it later for bound state dynamics, that's great. So that's exactly what we're going to do. Basically the mantra is we want to integrate out most of the gravitons and construct this effective two-body Hamiltonian. The reason I'm saying most of the gravitons is because we're not integrating out all gravitons. Some of them will eventually need to escape to infinity and describe the outgoing radiation. So those will not be part of our story. We will integrate out essentially off-shell gravitons. Now, this strategy is not indigenous to the two-body problem. It applies equally well to the to n-body dynamics, except that various details become somewhat more complicated. As we will see, this approach will indeed push the state of the art beyond what was known before this thing came along. This is version 1. Version 2, which is closely related, is rather than construct a Hamiltonian, which is still a gauge-dependent quantity, one can first construct some observables, which are gauge independent, and then either analytically continue those observables to bound observables, which is possible sometimes, and the sometimes is the subject of the star, or based on those observables, construct a Hamiltonian that reproduces them and then do the same, reduce the problem to the previous one, use the Hamiltonian to the bound motion. That's option 2. Option 3 is to construct something known as final state scattering observables or final state observables, which represent expectation values of operators in some final state. Notice that whatever I'm going to write here, I'm writing here on the right-hand side is not a normal Green's function, is not time ordered because the in and the out vacuum are both final states. So this is a little bit different from normal correlation functions, but they are not too different. One can construct these again using this is from the work of Casa or maybe and O'Connell. And one can construct such final state observables. And again, one can either analytically continue them to bound observables or again, reduce to the previous problem, construct a Hamiltonian and study the bound motion.
So a question, if you try to reconstruct a Hamiltonian, can you really fix it uniquely or is there some wiggle room?
No.
Because you...
No, there is a fair amount of wiggle room. Definitely, it will fix it up to canonical transformations, and you know, those canonical transformations could be a pain in the neck because they essentially make it very difficult to compare a Hamiltonian following from here, for example, with another one constructed by other means. And the Hamiltonians I'm going to show you later will be in a specific gauge, which is to say a specific choice of such canonical frame, and it's very different from the one that's typically used in post-Newtonian calculations from pure GR. And I will tell you exactly what, I won't tell you what the canonical transformation is, even though I know it. It's rather unilluminating. It's just long and ugly, and it eliminates terms that you don't like.
Okay, thanks.
All right. So our it's clear from this little discussion that the post-Minkowskian expansion or approximation plays on amplitude strength for a variety of reasons, if only because you know, post-Minkowskian approximation demands all orders in velocity. Amplitudes are typically relativistic unless you butcher them too much, they will give all orders in velocity. There are great perturbative tools to carry out amplitudes calculations. There are great techniques to integrate out gravitons, great effective field theory techniques, and I will say a few words about both of these. Now, to describe the dynamics of black holes, one would approximate them by point particles, if only because we believe they have no real internal structure when viewed from sufficiently far away. But one can perturb around that and give them structure by deforming these minimally coupled scalar fields, which are the point particles, with additional higher dimension operators, which would incorporate finite size effects and perhaps spin effects. So here is a brief summary of where we're at, and we are going to get to it. If I speak fast enough, I'm speaking a lot slower than I thought I would. So we have computed the two-body Hamiltonian to order g cube and part of the order g to the fourth. The calculations have been done for the contribution for the contribution of outgoing radiation to certain observables at order g cube. Certain dissipative observables have been computed at order g cube, and also certain spin-dependent observables and have been computed at order g square. And there is an interesting conjecture for an all-order relation between open orbit observables and pieces of scattering amplitudes. And last but not least, certain leading order finite size effects have been discussed, and a fair amount of structure has been identified in that. So this said, are there any questions? I will get back to some of these, though, of course, not to all of these.
Actually, can I just ask, following up on Maria's question, for the LIGO, do you want the Hamiltonian? Is that what you want? Sorry, can you hear me now? No.
On and off. So if I understood correctly, you're asking if LIGO needs a Hamiltonian.
Yes.
So LIGO needs a LIGO itself doesn't need a Hamiltonian, but the theorists at LIGO want a Hamiltonian because they want to take a two-body Hamiltonian and grind it through their machinery to produce signals for LIGO. That's why they need the Hamiltonian. I mean, we would be happy to give them something before the Hamiltonian because less work for us.
Yes,
but they wouldn't take it.
Okay, so exactly. And do they have does it have to be in a particular gauge? Do they? So you do need.
They don't. They are masters at constructing canonical transformations to whatever they want. They just want a Hamiltonian as long as it's a valid Hamiltonian.
Right. Okay. Thanks.
All right, so scattering and Hamiltonians. Well, in classical mechanics, which is basically what I had in mind up to now, is that we do talk about cross sections in classical mechanics, but ultimately everything is determined by the scattering angle. So if somebody hands you a scattering angle in classical mechanics, you nominally know everything if the dynamics is conservative. And in principle, you can reconstruct the Hamiltonian, but it's a little bit unpleasant because, well, you have to make an ansatz, you have to solve equations of motion, have to match coefficients, and so on. In non-relativistic quantum mechanics, the story is a little bit better, at least at Born level. So there we do talk about scattering amplitudes, and at Born level, there is a close relation between scattering amplitudes and potentials. They're just related by Fourier transform. So that, from a quantum mechanical point of view, if we know a Born level amplitude, we know the Hamiltonian to leading word. Field theory is very much closer to quantum mechanics than to classical mechanics. So scattering amplitudes are quite good. The problem or the issue is which part of them are relevant for our story. So the textbook approach instructs us to sum up tree-level and loop-level Feynman diagrams, and that will hand us the complete scattering amplitude if we're strong enough to add up everything. Now, usually it is said that loops are entirely quantum, and in standard field theory courses, we make an argument that h bar counts the number of loops. We put e to I over h bar s in the path integral, and we see that h bar counts the number of loops. So the question is, do we just toss away all the loop level Feynman diagrams and restrict to tree level if we care about classical limit, or do we do something else? Well, the answer is that we have to do something else because h bar carries dimensions, and sending a dimensionful quantity to 0 is usually done with keeping something else fixed. Otherwise we just change our meter stick. So so there are several classical limits that one can take. For example, one can take h bar to 0, keeping p over h bar or h bar over p fixed. So that would be the de Broglie wavelength. And this is indeed what goes on when we talk about classical limit in usual quantum field theory courses with h bar counting loops. This is exactly what happens. It takes us back to just the Born tree-level amplitude. However, there are other limits that one can take. For example, one can send h bar to 0 while also sending the de Broglie wavelength to something, well, not to 0, because again, it's a dimensionful quantity, but rather make it much smaller in this limit than, say, the impact parameter. If that's the case, the limit that results from here is different from the former. And it turns out that parts of loops survive. So we are going to talk on the next slide a little bit more about this, but as a preview, it has to do with, it's very analogous to what goes on, for example, in ADS-CFT when we talk about the large charge limit on the worldsheet. There we take, when we talk about the large charge limit on the worldsheet, we take something that's very quantum mechanical and turn it into something that's classical. So this said, let's talk a little bit about that. So in this limit, which I'm phrasing now in normal units, h bar equals 1. So the de Broglie wavelength, we want it to be much smaller than the impact parameter, and the impact parameter is of order of 1 over the momentum transfer because they are just related by Fourier transform. So in this classical limit, the angular momentum, the orbital angular momentum, which is just b cross p, happens to be much larger than 1. So this will be our a characterization of this classical limit in, if you wish, in natural units with h bar equals 1. One can make exactly the same argument for a spinning body. There's a de Broglie wavelength for associated with the spin motion, and as long as this is much smaller than the size of the object, that should be a classical motion. And one finds that for this, the spin has to be large. So the expansion or the classical limit that we are interested in is that 1 over L is of the order of 1 over S is of the order of Q over M, where Q is the momentum transfer. In particular, Q times S is of order 1 in this classical limit. So with this together with the fact that the Newton potential is classical, G over R is classical, is enough to tell us what's the structure of the potential if there is a potential that captures the conservative scattering. And it looks like this. The first part has to do with the Newton potential, and basically Newton potential to whatever power you want, because that's also a classical quantity. The second one has to do with presence of spin. As I said, Q dot S is of order 1. And then the last factor is related to finite size, and which I haven't quite discussed yet. So a little bit annoyingly, perhaps, if we want to describe the classically spinning bodies, we would need a field theory of higher spin fields. The reason this is annoying is that we don't have a consistent field theory of higher spin particles, at least not with finitely many of them. But if I get to talk about this, I will we'll see how we go around the various no-go theorems related to this. So here is an example of how we extract the classical potential. Again, in the Born approximation, we have 2 particles. We scatter them. The 3-level scattering amplitude is known. In this limit, basically, we lose any distinction between P and P prime. So the vertex up here and the vertex down here, they're just the stress tensor of one free particle with momentum P. We contract this. It's just T mu nu up here, T mu nu down here. There is the 1 over Q square propagator. We Fourier transform this, and this it hands us the potential. I'll show you the potential in a little bit. It looks like 1 over R, just like the Newtonian potential, and then some numerator that's function of velocity. It starts with 1, just as Newton instructed, and then it contains a term of order V square, which is what is the first post-Newtonian correction due to Einstein and Infeld, and then it contains an infinite number of additional corrections. So to go beyond 3-level, we need to be a little smarter, because well, the construction, the one loop amplitude, with the classical part of the one loop amplitude, has something that one might call pathologies. It contains a piece that looks like the 3-level potential square, or the 3-level amplitude square, and it scales with the momentum transfer in a way that's not classical, but rather it's super classical. So that has to be eliminated, and that has to be eliminated consistently. So the way we do this is we construct an effective field theory, whose purpose in life is to have 2 properties. One is that it scatters only particles, because in the classical limit, antiparticles are very massive, or at least they pretend to be very massive. They are, of course, the same mass, but they just pretend to be very massive. And loop by loop, the scattering amplitudes of this effective Lagrangian, they should reproduce the classical limit of the complete scattering amplitude of the full theory. So this is how that Lagrangian looks like. So we have 2 particles, A and B, that we scatter. They propagate only positive energy poles, these ones. And then there is an interaction potential here. Is basically a 4-point interaction with a non-local coefficient. And the goal is to find this, and we find this by matching the scattering amplitudes coming out of this Lagrangian with those of the full theory. Once we have this, the classical Hamiltonian is obtained by just stripping off the A's and the B's, and it's just that one. So that's ultimately the goal, to compute this thing. So now that we know what we want to compute and how we are getting to it, let's talk a little bit about how to compute scattering amplitudes without much pain and suffering. But before that, are there any questions? All right, so how do we compute scattering amplitudes, and especially gravitational scattering amplitudes, without much pain? So the textbook approach is that it has always been write down Feynman rules, construct Feynman graphs, add them up, and pay the price. It gets hard at sufficiently high loop orders, and for gravity, that high loop orders is typically 1. So we want to go beyond 1, so we need something better. And this, of course, has been the subject of active developments for the better part of the last 20-some years. And the key for progress was not to build better computers, though that does indeed play a role, but rather to focus on the analytic structure of amplitudes, and especially of amplitudes integrands. Now, of course, focusing on the analytic structure of amplitudes is important, and it has a place, but not in our story today. Today, we will play with amplitudes integrands and their analytic structure. So they are,
Sorry.
Yep.
So can I ask you, how do you avoid the renormalizability problems, the divergences that are going to crop up in loops? Yeah,
that is a wonderful question, and the answer is classical limit takes care of them. It just tosses them out. And to see this is involves the third branch that I didn't mention here. So there is, if we have a quantum scattering amplitude, we have many limits that we can take. The one that we are going to play with is the one in the middle, in which h bar is 0, and that will give us something. There's another limit that exposes the UV divergences, which is h bar is fixed, and these wave numbers are large. And that is indeed the limit that exposes the short distance properties of gravity, but these two are actually disconnected. So we will construct an integrand, a regularized integrand, which is finite because it's regulated. But if we were to integrate it, we would see the divergences in the usual 1/epsilon fashion. But as we take the classical limit, all the divergences will be essentially removed, and the stuff that remains is very finite. There will be some divergences at 3 loops that we're going to encounter, but those have nothing to do with UV. They are infrared divergences.
Okay, thank you.
So sorry. So first you introduce UV regulator, and then you take H to 0. Don't you have the problem of ordering of limits?
Ordering of limits.
Yeah.
I thought you might ask ordering of limits, Sergey.
Right. So you have actually 2 regulators, right? UV, IR, and then you also have H bar, and you set first H bar to 0, and then you remove all the other regulators.
So the IR, okay, I did mention an infrared divergence, and as I said it, I was wondering if anybody would catch me on that, and you did. So there are infrared is really regulated by the fact that we are scattering massive particles. So there is no honest infrared divergence in this amplitude. The reason we will have an infrared divergence is because we are focusing on the conservative dynamics and the fact that, basically something that can be described by a potential. That's the origin of the divergence that we will encounter. But you are correct, that will be regulated by the same epsilon that in the full theory would regulate also the UV. Yes, the limit will involve the order of limits that we're going to pick is h bar to 0, and then epsilon will be removed because it's not there anymore. Now, one could attempt to do the other way, and of course we can't do that too high a loop order, but we could do that at one loop, for example. And the story is a little bit different. There are differences, and it's worth talking about those differences, but can we postpone this for after the talk?
Okay, sure. Thanks.
It's a long story. That's what I mean.
Okay.
Yeah.
Thanks.
Where were we? Right. So how do we compute amplitudes? Right. So the methods that. Okay. So since we will be focusing on amplitudes integrands. Integrands, just as implied by Feynman rules, they are rational functions. So their analytic structure is not terribly complex. It's just poles, and it's just given by their poles and residues. And so the idea is to reconstruct these rational functions from their poles and residues. The poles are prescribed by the fact that the vertices are local and all the poles come from Feynman propagators. And factorization of tree-level amplitudes and more generally of amplitudes integrands implies that the residues have a very simple structure. They're just products of lower loop amplitudes, or depending on how many on what kind of poles we're looking into, they will be also products of tree amplitudes. So that's the story. Ultimately, the tree-level amplitudes, which are the simplest amplitudes, will be the building blocks of other higher loop amplitudes, at least to the extent that we're interested in today. And there will be a few interesting new methods that that will be used that have been developed to construct tree amplitudes, like the on-shell recursion relations. And their assembly into loops goes by the name of generalized unitarity. And to deal with the fact that gravity is complicated, we are going to use the so-called double copy construction, either in the form of Bern, Carrasco, and Johansson, or in the form of Kawai, Llewellyn, and Tai, depending on what is more useful for us. So here is how it goes. Imagine that we want to construct the integrand of a one-loop amplitude. This here denoted as a 6-point amplitude. Well, this thing will have a number of propagators, and if we're close to 4 dimensions, we can have 4, at most 5 propagators. I drew here only the 4 kind. And we could construct the residue of this pole by multiplying the 3 amplitudes corresponding to the shaded blobs. Now, there is a residue also for 3 propagators, for a singularity corresponding to 3 propagators. This one will, in some sense, be non-local because it will contain information about the 4th propagator that's captured by the first one, but it also will contain polynomials which are not captured by this. So ultimately, this second residue will capture those guys after we subtract the contribution of the ones of the residue of the first time. And last but not least, there are also graphs with 2 propagators and no other singularities. Again, multiplying these trees will give us a number of non-localities which are eliminated once we subtract the contributions of the poles of the first and second kind, and that would be the contribution of the bubble type integrals. And when everything is put together, making sure that all combinatorial factors and so on are taken into account properly, out comes the one loop amplitude in this case. But of course, this is not restricted to one loop. One can proceed to 2 and 3 loops and even higher. I think the current record is about 6, I believe, at least in this kind of approach. So this is, if we pause to think about this, it is not difficult to see that this is ultimately just a reorganization of the usual Feynman diagrams, and that that reorganization captures the analytic structure of the Feynman integrals, and to a large extent, it represents a generalization of the usual optical theorem. It's a generalization in the sense that it adds more information to the optical theorem. The optical theorem just talks about the discontinuity of an amplitude, but it doesn't tell us much about the structure of the thing which once integrated gives us S. Here, we are building in information coming from Feynman rules that this S matrix is an integral of rational function with prescribed poles and residues. So this said, we will be interested again in just the classical part of amplitude. So that will allow us to eliminate a whole bunch of these unitarity cuts. In particular, in the classic, we are interested in the classical amplitudes that describe long-range interaction between the two bodies. Therefore, we should not be interested in pieces of amplitudes in which the two bodies sit on top of each other, like these. So we should forbid unitarity cuts that, we should forbid poles that that represent Feynman diagrams or integrals that that have this structure. We should also forbid diagrams that would contain, for example, just graviton self-energies. The reason is, at least on an intuitive ground, that this has nothing to do with classical interactions of heavy bodies, but it has to be something that's quantum mechanical. And this indeed relates to Sergei's question and the question before that, in the sense that clearly these guys would be divergent. So what happens if we first take these and compute them and then take h bar to 0 in the sense that we described? If we did that, then these guys would still be tossed away by the classical expansion. They will just have they will not have the right 1/, angular momentum scaling too, or if you wish, the scaling, they will have the wrong scaling with the transfer momentum to be classical. And last but not least, we are also going to toss away unitarity cuts that correspond, that would capture gravitons that start and end on the same matter particle. The reason is, again, that intuitively this cannot be a potential, but rather it represents the a correction to the interaction of gravity with a single particle. So this is, and again, one could wonder whether this is also something that would cause issues with the classical limit, because this form factor type calculation would necessarily produce divergences, and one can compute, say, for example, just the cap here and take the limit afterwards and see that it goes away. So this said, we are back to computing this, the remaining pieces that go into this calculation, which are trees. Again, the Feynman graphs would be complicated. So here you have a three graviton vertex, which has about 100 terms, but it has one, and of course the 4-point vertex has many more terms, but they all have, the 3-point one has a remarkable property, namely that if you put the external lines on shell and contract them with polarization tensors, then this is what happens. It factorizes into a product of three gluon vertices. So this is the field theory realization of an observation originally made in string theory due to Kawai, Llewellyn, and Thai, that tree-level gravity amplitudes are linear combinations of products of gauge theory, Yang-Mills theory amplitudes. There is a little bit of a story that goes in here, which is that just as it happens in string theory, in field theory also, the graviton comes with friends, with the dilaton and an axion. And to actually get just Einstein gravity, as opposed to what goes today by the name of n=0 gravity, requires us to remove the dilaton and the axion. And this we can do. Now, another, this is, of course, a valid approach, and it has been used to great effect to compute loop-level gravity amplitudes. But it does have one problem, namely that in this product of amplitudes, the pole structure is superficially messed up. There are double poles For example, in the first line, there's a pole there's a 1 over s square pole in this product, which is cured by the coefficient here. But this kind of cure is less obvious as the number of external lines grows. So a much more efficient approach is the one based on the idea of color kinematics duality, which requires us to take gauge theory amplitudes and organize them in a specific way, namely, whenever the color factors of the gauge theory amplitude obey some algebra relations, like the Jacobi identity following from the Lie algebra of the color Lie algebra, then the corresponding numerator factors, kinematic numerator factors, will obey the same relation. So this is not obvious. It's not obvious that this can always be done, but a proof at tree level has been discussed, has been constructed. Now, once we have an amplitude in this form, then a gravity amplitude can be obtained by simply replacing the color factors with another copy of these kinematic numerator factors. They don't need to belong to the same theory. The only thing they need to is to obey the same algebra relations as the color factors. Now, why is this? A gravity theory is not obvious. One can, of course, construct examples, but this is not really a proof. One can, however, prove based on just the structure on this slide that the result, and this M4 and anything with more points constructed in the same fashion, will be diffeomorphism invariant to all orders in perturbation theory. So this is a proof that these are amplitudes in a gravity theory. Now, this is not something particularly special. There are lots and lots of theories that have this structure. So here is more of an advertisement than anything else. So let me skip it because I'm running out of time. Now, about the projection of the dilaton axion, the idea is that when we construct these the residues or the generalized cuts that I discussed, to project out the dilaton axion, all we have to do is to keep track of what physical polarization we are summing over. And in a four-dimensional helicity notation, all we have to do is correlate the left and the right amplitudes to have exactly the same helicity. So instead of getting, say, a positive helicity gluon, and so a positive helicity gluon in one copy and the positive helicity one in the other gives us a graviton of polarization +2. Both of them down give us polarization -2, and the ones that we're forbidding is one up, one down. And those would be the dilaton and the axion. So doing this, and in a dimension-independent form, we demand that these amplitudes obey a slight generalization of the usual word identities. Doing this, we project out the dilaton and the axion. So we are almost ready. We are actually ready to put everything together. But before doing that, I would like to say a few words about another. Let me skip that. And you can ask me about other applications of color kinematics, which could have some bearing on the two-body problem. But feel free to ask me about this later on. So let's put everything together. So at one loop, we are interested in looking at just these cuts, because at these unitarity cuts, the reason is that if we were to allow this propagator to collapse, then we would be capturing graviton bubbles, and we don't want those. And similarly for the second one. Of course, this does contain the other unitarity cut in which there is a matter propagator that's also set on shell. At one loop is these two. At two loops, it's not entirely obvious, but there are these three pole structures that we're interested in. At three loops, there are 8 of them, and the number grows not as fast as the number of Feynman graphs would grow, but the number of relevant cuts still grows. So the story is basically what I just said. Compute, these are the poles. The poles are read from the cuts. The residues are computed by multiplying the relevant trees. Everything is shaken into a form that resembles Feynman graphs, and then integrated, or at least prepared for integration. Then the result is matched onto the effective field theory, and out comes the Hamiltonian. And again, just to recall, the Hamiltonian is on the first line. We are after these C1, C2, C3, C4, and perhaps the higher ones in some future. So C1 is contains Newton's potential, Einstein-Infeld correction, and also a slew of other ones, and has been known for a very long time. C2, which is the order G square correction to, or the second post-Minkowskian correction, is slightly more complicated and was computed by Damour in, mid 2000s. And then this is our work done in collaboration with Byrne, Chung, Solon, Shen, and Zhang. This is the order G cube correction. It's here, and a more recent work with Byrne, Para Martinez, Ruf, Solon, Shen, and Zhang is the potential at order G to the fourth. So let's talk a little bit about G cube. The variables are defined at the bottom, but you really don't need to worry too much about them. Sigma contains the entire velocity dependence, is the product of the momenta of the incoming particles, and everything else is just masses and energies. The only non-trivial function is this logarithm here. It's a little surprising that it's just a logarithm, given that it comes out of a two-loop gravity calculation, but perhaps it's not entirely surprising from a classical gravity point of view. Now, at order G to the fourth, the story is more complicated. Here, I'm showing explicitly the contribution from the subtractions related to the EFT construction. The amplitude is given by the pieces on in the first term here. The thing to notice is the presence of a 1 over epsilon. And again, this is not, as I was mentioning a little earlier, this is an infrared divergence, and it's not an infrared divergence having to do with the actual infrared divergences, but it's an infrared divergence having to do with the fact that we are demanding that everything fits, that this scattering is described by a potential. So we are not including certain kinds of gravitons in this amplitude. In particular, though, we are forbidding those that could potentially go on shell.
Sorry, how can you tell it's an infrared divergence? I mean, from this, it looks like it could be either.
Yeah, it looks like it could be either, but we can tell it's an infrared divergence because we actually can look inside the integral, and we can scale the integration variables, make them, for example, large, and there is nothing there. This comes from the regions of small momenta, of small loop momenta.
Okay, all right, thank you.
Mm-hmm. All right, so again, if we included in the calculation gravitons that are allowed to go on shell, then this 1 over epsilon should go away. However, once we do this, it's not entirely obvious that everything can still be described by a potential. So at least for the time being, this is what we did. So just to show you how it actually looks like, we have slightly more complicated functions. There are some more logs, but now we also have dialogues and also elliptic integrals of the first and second kind. So this is what I was saying a little bit earlier, that we demanded that everything that we computed fits inside a potential, but the potential does not describe the complete conservative physics. There is additional stuff that does not correspond to radiation escaping to infinity, which is also conservative, but it's not a potential. And that is responsible for curing this 1 over epsilon. We don't have that one yet. Needless to say, if we take any one of these and expand in a PN expansion, then we will recover pretty much everything that is known in the post-Newtonian approximation. So the question now is, after all this song and dance, to what extent is this relevant for LIGO? And we're not quite equipped to do this, but LIGO theorists are equipped to do this. So shortly after our GQ paper appeared, a number of LIGO theorists took our result and compared with various post-Newtonian and post-Newtonian approximations fed through their machinery, which goes by the name of the effective one-body theory, and also compare that with the numerical GR. So here is a plot of their result. The teal line is numerical GR. The plot shows the binding energy of a binary of equal mass, and is plotted against the orbital frequency. The teal line is numerical GR. The various lines at the top are various post-Newtonian approximations that were available at the time, and the result coming, the simulation coming using the 3 p.m. our 3 p.m. Hamiltonian is right here, and it matches numerical GR quite a bit better than the various other models within the approximations that have been used in this simulation. In particular, they did not include outgoing radiation. So because of this is not 100% conclusive and applicable to LIGO, but they themselves found that this agreement is encouraging enough to warrant effective one-body theory resummations of post-Minkowskian approximation. So this is one bit of implication of our two-body Hamiltonians for LIGO. Now, the same cannot be done for the 4 p.m. or the g to the 4th Hamiltonian, again, because of the 1 over epsilon and the associated scheme dependence. However, they, the same group, or almost the same group, they still tried, and they made some choices about how to deal with the 1 over epsilon and the scheme dependence, and the choice involved just dropping it. And here is what they find: the same plot, the same kind of plot, binding energy versus orbital frequency, the same mass ratio. The newer 4PN effective one-body theory is the dashed red line, numerical GR is the black line, and this approximation to the 4 p.m. Hamiltonian is the golden line. It comes pretty close to the 4PN EOB approximation, and in various places it is a little bit better, though perhaps not at the very end. Still, this is not, of course, this is not conclusive, but it is quite encouraging, and it also is a motivation to finish the calculation of the various other terms, including those that eliminate the 1 over epsilon and the scheme dependence. So this is all I meant to say about spinless scattering and its contribution to two-body potentials. I also meant to say something about spin, but I did run out of time. So let me skip that part and conclude with 2 slides, one on the emergent structures in the two-body Hamiltonian, and this will include also comments about the stuff that I haven't talked about. So by looking at the post-Minkowskian approximation, we found a collection of non-trivial functions which appear in observables or in the Hamiltonian, and consequently in observables of classical two-body motion. One can in fact proceed and say that, and state that all the non-trivial functions that appear, they are related to specific non-trivial Feynman integrals that appear in such calculation. And one can classify the type of integrals that can appear. One could use this as an ansatz for matching the numerical numerical GR calculations, and this way bootstrap for example, to even higher orders in GN, a Newton's constant. There is something I didn't talk about that did come out of calculations like this, is that there is a direct relation between the scattering angle and scattering amplitudes. There is one that has been known for a while, and it involves the iconal phase. But there is a slightly different one that, again, I didn't talk about, but it did emerge out of these calculations. Related to spin, there is more structure that appeared. There is a function here called delta, quite analogous to the iconal phase or to the logarithm of the amplitude, which is a sort of generating function for all observables. Here, O stands for some observable. For example, for the momentum, this is just a derivative. For the spin, this is the spin operator. This D is a certain differential operator that talks to the spin and to the orbital angular momentum. And this commutator is a commutator in the usual sense for spin operators, and it's a Poisson bracket for momenta. So there's a single function which appears to characterize the complicated dynamics of two spinning bodies. The reason I'm calling it complicated is that, unlike the spinless bodies, now for which scattering is in a plane, now we have two scattering angles because the scattering is no longer in a plane, and also we have additional observables having to do with the spin. So essentially, 5 observables, they all follow from a single function, the logarithm of the amplitude. There are certain open orbits observables which can be computed in terms of scattering amplitudes, which is and to the extent that they have been computed, they are related to they are the same as what comes out of Hamiltonian type analysis, but they also contain additional information like the effect of outgoing radiation. And last but not least, certain open orbit observables can be obtained by analytic continuation in a way that I have not described, but this is from the work of Kalin and Porto. So with this, let me end here with a few words about the prospects on the classical two-body problem from a scattering amplitudes perspective. This approach is guided by gauge invariance, and because of this, it produces results in a relatively simple form. So actually, this is related to Mario's question from before about gauges. So here, this Hamiltonian is, of course, in a specific gauge. Hamiltonians, which are usually used in the post-Newtonian approximation, they will have a collection of terms that look like momentum dotted, center of mass momentum dotted into R. So here, there's a canonical transformation that removes those and produces this gauge, which is called the isotropic gauge, and which doesn't have those terms. So because this approach is guided by gauge invariance, it produces perhaps the simplest form of Hamiltonians. The methods that I described apply for lots and lots of problems, not just the spinless case that I discussed in details, but also for spinning bodies, and also for tidally deformed bodies, and also if one cares about outgoing radiation. The methods are far from being exhausted, but there is a bottleneck, which is common to pretty much all methods that are based on scattering amplitudes, namely integration and higher order integration. Luckily, there is a wealth of QCD experience that is brought to bear. And it will continue to help us at least for another order or two. The results that I described do push the state of the art for LIGO relevant calculations, and also provide theoretical data for understanding the structure of solutions solutions of the equations of motion for the GR two-body problem. I'm referring to the structure discussed here, and also the various interesting functions that appear in the result. And again, similar methods can be applied to the relativistic n-body problem if one is strong enough to actually carry out the relevant integrals. So in short, it's we should expect more results in this direction in the future, perhaps not too distant future. And on that note, thank you very much, and apologies for going over time.
No problem. Thank you very much for a very nice talk. Are there any questions?
Maybe if I can ask just for clarification, in your spinless case, you treated the spinless system as a minimally coupled scalar field. Was that correct?
That is correct. Yes, it's just a minimally coupled scalar.
And just why was it minimal rather than some other coupling to the curvature?
So couplings to curvature, there are arguments based on word line approach that higher derivative couplings like the ones you just described would well, they describe a a larger body that is deformed because of the ambient gravitational field. So this is what I meant. Inclusion of operators like the ones you mentioned would capture this tidal deformation that I mentioned here. And indeed, pretty much everything I said can be applied to those to such systems as well. In retrospect, exactly why a minimally coupled scalar, one could try to wave hands and say, well, Birkhoff's theorem says that from far away a black hole is has no structure. It's just it's spherical and it behaves like a point particle. There is, of course, also an a posteriori argument that says that pretty much everything that I discussed here, one can attempt to compare with results done for actual black holes in actual general relativity, and everything matches on the nose. So that would be a confirmation of the, if you wish, of the assumption that that black holes could be described this order by point particles, with minimally coupled point particles.
And the second question is with regard to the scheme dependence. How serious a problem do you think that is? Or by the scheme dependence, you mean presumably that you did dimensional regularization and minimal subtraction or something like that?
No, that's not what I mean. No, I mean something a lot more benign. What I mean by scheme dependence is this mu here, right? So when we do dimensional regularization, we have to introduce the scale to soak up dimensions and write with the
it's still related. Yeah, it's
log of p square over mu square. Right. Yeah, so it's this one. This is what I meant by scheme dependence. Now, once 1 over epsilon is cancelled, there won't be any anything coming out of the scheme of coming from this mu dependence, just because there is no 1 over epsilon to hit the epsilon that comes out of this, of the expansion of the numerator here. So I am quite confident that once this is cancelled by inclusion of, like I said, radiation type effects, which are still conservative, namely, gravitons that go out for a while and then they are reabsorbed by the binary. So once we include this, this 1 over epsilon will go away, and consequently, the mu dependence will also go away.
Okay. Thank you.
Can you do the same calculation in ADS?
How much time do I have?
No.
The short answer is not easily, just because ADS calculations are never easy. Well, the short answer is I don't really know. I don't really know how to set up a normal scattering problem in ADS space. That's what I really mean. And what would be the interpretation of the most naive thing, which should be more or less like the usual correlation functions in ADS-CFT. That's what I mean. It's maybe just you know, my ignorance on the matter.
Well, 4-point function, isn't it?
He's using in propagators, or out, I should say.
No. This is standard Feynman diagrams. This is standard Feynman diagrams. The in calculation, that's a different story. It involves these final state observables. So this, what's done here, what I described is, regular Feynman diagrammatics. Propagators are 1 over p squared plus m squared minus I epsilon.
You're saying you would know how to do that aspect of it in ADS?
Yeah, that aspect I know how to do. It's just that it would have to be done in position space rather than in momentum space and so on. But my problem is in what sense can I interpret this as a scattering problem? I mean, what we extract out of 4-point functions in anti-de Sitter space is not really a correction to something that could be described as two-body motion, but it's more something that lives on the boundary of anti-de Sitter space. That's what I mean. So
no. People know how to take a limit and reproduce scattering amplitudes in flat space.
But there's no on-shell methods.
Yeah, well, they can be invented. They can be invented. There is,
right.
There's this,
early days.
There's this split representation for propagators, which is quite reminiscent. Unfortunately, it's not identical because, it talks about complex anomalous dimensions in some sense. So it's not. Right, so the things that propagate to the boundary in this split representation of the ADS propagators are not only the things that would be interpreted as operator insertions on the boundary, but there are also normalizable modes. But yeah, it's close, but not quite.
Actually, I have some more related to your talk question.
Okay.
So you see this infrared divergences only at 3-loop order?
Yeah.
So is there any simple explanation why it is so late?
Yes, it's because so there is. They could have appeared at 2 loops. But they don't. So let me try to get rid of this pointer and try to draw something. So they could have appeared at they could have appeared at 2 loops, but they don't. So here is a picture of something that one might think as a 2-loop amplitude. All right, so this is a, and here is a weak graviton, either this or this. Sorry, I don't mean a weak graviton. So we did not include these guys. And in here, we did not include, well, we did include these guys. It turns out that this diagram has a real and an imaginary part, and the imaginary part has to do with this thing going on shell, and the real part is what contributes to the potential. This part does not contribute to the potential, but because it doesn't contribute to the potential, because if this were an off-shell graviton, then this interaction would be instantaneous, so there is no time for emission of these 2 additional gravitons. But the graph on the right and also the graph on the left, they could in principle be interpreted as a graviton being emitted from binary at some point and then reabsorbed by the binary later on. It so happens that this does not cause a divergence at two loops. Ultimately, the reason being that everything that's captured by these is part of some imaginary parts. Actually, this one also, if you were to compute it exactly, this one is purely imaginary. The analogous objects at three loops, they look more or less like this. And now there is the option for a lot more gravitons that could be on shell. So all of these guys. So if one looks at this binary from far away, it would look something like this. So from an effective field theory point of view, one would need to look at this kind of diagrams with this graviton being close to, by, can you see my mouse?
Yeah.
Yeah, so this graviton being close to one shell, this one close to one shell, this one close to one shell, so they propagate for a long time. And this is diagrams like this are the origin of diagrams like these are the origin of the 1 over epsilon of the divergence. So like I said, they could have appeared earlier, they don't, because features like this at one loop below, they are purely imaginary and actually have to do with just emission of radiation.
Okay, thanks.
Can I ask, actually, if there were corrections to Einstein gravity, you'd presumably be able to include them, right? And we just include the tree level amplitudes or anything like that.
Yeah, that's right.
And do you know like where you would see them first? Is there some way of classifying where you would see them?
Yes. So okay, so it depends what kind of okay, so if we are talking about corrections to Einstein gravity, in the form of say an R² operator, or maybe an R to the 4th. Hey, where is my mouse? Right, so imagine that we have an R to the 4th, right, as we would get in string theory. So a correction like this, pardon me. So a correction like this would appear through a graph of this type, because there are 4 gravitons. So it depends exactly how you choose to call this, but the order, or at least the loop order at which it first appears, it can be read from just the operator itself. How many gravitons does it have? If it's a purely gravitational term, it has to sit in the middle, just connect it to everything else, count the loops. That's yeah. One can start debating at which order in the Pn expansion it would contribute, or which order in the Pm expansion it would contribute. But then the coefficient here starts, to actually put a number next to that order. The coefficient here needs to be specified completely. That is also what its G dependence. The velocity dependence can be read from this, but to actually assign an order, at least a Pn order, one would need this one too. For a PM, one can be a little bit glib and say, well, gee, this is 2 loops. So I don't know. if this coefficient is of order 1, then this is just G cubed. So Sergey, about your order of limits question.
Right.
I did not forget. I was.
Well, you kind of answered to the question.
Yeah, I don't. I can give many pieces of what explanations about many pieces of what happens here and there. We haven't done a very coherent study of exactly what happens here. But you are indeed correct. We're taking the limit h bar to 0 at finite epsilon, and then epsilon goes away, and we.
Actually, maybe a related question. kind of general question. You use one and the same regulator for both UV and IR. Why is it allowed?
So again, this is it's not, well, on the one hand, it's the feature of dimensional regularization. But again, this IR is not, the IR that we have here is not the usual IR. The usual IR is regulated by the masses. So
wait. Why by the mass? You have gravitons in the loop, and gravitons have no mass, right?
well, that is correct, but that is correct. But the momenta that we allow for the gravitons, we allow, okay, so we don't allow our gravitons to get close to on shell, because if they do, then that's not part of a potential that's related to emission of radiation. So all our gravitons are far from on shell. And in that regime, their Q square is never zero. Therefore, there is no room for infrared divergences to appear.
So you have a cutoff kind of from below.
Yeah, there's a cutoff from below, if you wish, though there is no there's no there's no hard cutoff. It's not that the momentum is larger than something. It's just that there is an imbalance between there's an imbalance between the energy part of the gravitational momentum and the space-like part of the gravitational momentum. And that is enforced via, in the calculation of integrals, by demanding that the matter particles, they are close to their shell. Because ultimately what we want is, again, classical heavy particles. Classical heavy particles, we're not going to see Earth going off shell anytime soon. So yeah, that's why the matter particles are always close to their shell, and that forces the graviton to be far from their shell, because at 3 points it's clear why that's the case, and right, you don't satisfy the momentum conservation. And for higher points, it so happens that the integrals that appear have the property that all the gravitons will be far from their shell. So this, I'm saying very many words about something that in the QCD literature is known as the method of regions. And so the short answer is we are integrating in the potential region, and the potential region is ultimately defined as, the set of words I just said in the last 5 minutes. It's the gravitons are far from on shell, matter is close to on shell. There's a specific scaling that one can assign to this, but the bottom line is just that the gravitons are far from on shell.
But you're sure that overlapping divergences don't cause a problem there? Because you're getting these things occurring at higher orders and higher loop orders, and it seems more subtle to me.
So am I going to bet my life on it? No. Am I going to say that I'm sure? Yes. Yes, I am pretty sure. The reason ultimately is that the graphs with infrared, with overlapping divergences, again, they are quantum mechanical, and we could, in principle, track them. And up to some loop order, we did not at 3 loops, because that's far too hard. But at 2 loops, we did go through the exercise of tracking some graphs with ultraviolet divergences, including at least overlapping divergences that would formally of this type. Sorry for the drawing, but again, these are if we cover the blob that contains these divergences, this is again a self-energy correction to the graviton, so it's not something that should exist in the classical limit. And indeed, if one does the Gedanken calculation of actually writing down what this means and see how it scales with this with a momentum transfer, which in this case would be the momentum of the incoming graviton, then it's far too quantum mechanical to contribute in the classical limit.
doesn't seem overly convincing when that is embedded deep within a higher order graph.
So, right. So this is again something related to stuff I did not say because I did not want to go into too many details. But there is, I don't know why I cannot draw properly here. The reason I can't draw properly is that my mouse disappeared. So let me, sorry, I can't draw, but let's imagine for a second that we have this this graph, the self energy that's there, and it's embedded in a bigger graph, and also that we have some momentum transfer which is small by the definition of small that we have. Then because of this, ultimately all gravitons that are exchanged between the two matter particles will have to have commensurate momenta, because if they don't, then that would not be part of the region that we're integrating in. Right. So again, I did say that the momentum transfer is small, but ultimately graph by graph, and if you wish, exchange graviton by exchange graviton, the momentum has to be of more or less the same order with the entire momentum transfer. Otherwise, it is not part of this momentum region that we're integrating over. Yeah, so this does take care of the fact that, indeed, in principle, if we were to integrate over everything, I would agree with you that there's a problem. There could be a problem with this being embedded in a bigger graph, and then this momentum is arbitrarily large and so on. But again, because of the region that we're integrating in, the momentum that flows through along the arrow that I drew is never arbitrarily large.
Yeah, I suppose I'm worried that the non-renormalizability of gravity could be hitting you. And this would be in contrast to QCD, where you have complete control over that separation of scales, as you mentioned. But I accept that you've done the calculations carefully.
Thank you.
Any further questions? I also have to go soon. So, but thank you very much, Radu, for the very nice talk.